Hello, we are Team Parsons Brinckerhoff, and today we will be presenting our construction improvement proposal for the LA Rams Stadium project. The purpose of this presentation is to provide our professional opinion of the efficiency of a specific construction activity of the project. Based on any flaws that we find in the construction analysis, we will be providing our own improvement suggestions that will better improve the activity's productivity. Before that, a brief overview of the project. The LA Rams Stadium is a $4.6 billion project located in Los Angeles, California. The general contractor is Turner Constructions, and they've graciously provided us with the footage that we've used to analyze. Here's a quick preview of that footage. And with that, let us begin our report.
The project, LA Stadium Entertainment Center, is a retractable roof stadium and entertainment complex district under construction. It's located between West Century Boulevard and Pinckney Drive, Inglewood, California. According to our observation on April 13, there was a crew working on geotextile stabilization activities. This activity involves laying geotextile fabrics material on a previously grade ground. Also, the material has to be overlapped and secured to each other. In terms of the operation, we observe first that the workers set up the truck with a trailer roll dispenser in a perpendicular way to the area where they are going to set up the geotextile. Second, they place the geotextile. Third, they align the geotextile, cut the geotextile, and then secure it with stakes. Last, they move the truck to the next point by the width of the roll. We identify of the material that the crew were using a geotextile, a type of geotextile that we couldn't identify because of the quality of the video, and they were using stakes to secure the geotextile. In terms of the equipment, we observed that the crew were using a truck attached with a trailer roll dispenser to help them to support and transport the geotextile. The crew also were using a hammer and a cutter to cut the geotextile and secure it. Also, the workers were using helmets, gloves, vests, and glasses.
The weather conditions of Hollywood Park, California on April 13, 2018 were favorable for construction work. The temperatures stayed within the ranges of 57 to 78 degrees Fahrenheit throughout the day with no precipitation. Humidity was low at around 18%, making site conditions relatively dry. Wind at the site was not a factor and posed no issues to construction activity. Wind speeds were measured to be 3 miles per hour max to the northwest. At night, temperatures dropped down to around 62 degrees Fahrenheit throughout the night. The site itself was organized and there were no instances of congestion or cluttering on the roadways. The roadways for construction equipment to be transported path around the perimeter of the site. Construction materials are stored directly on the path that the vehicles travel along, helping to reduce clutter and cut down on possible safety hazards on the site. The soil on site is primarily a silt loam. Silt loam is composed mostly of sand and loam with a smaller percentage of clay.
To gather our data, the following approach was taken. We used a webcam provided by the LA Rams website that featured live footage of the construction site. We focused on the particular activity that was going on the north side of the construction. We were able to zoom in this particular activity, and we observed that a crew of 5 laborers and 1 driver. To determine the total time it took the crew to perform a whole cycle, we used a timeline to determine how long it took a crew member to complete the task for this particular activity. After gathering our data, we used three methods to analyze the task. These were the crew balance chart, flow diagram, and process charts. A crew balance chart represents the performance of each crew member and piece of equipment involved in the task with respect to time. A crew balance chart helped us to analyze the productivity of worker-machine combination, as it demonstrates the interrelationships among the number of crew members and the resources available at the job site. A flow diagram is a line sketch that shows the movement of people and things at a job site. In general, a process chart will follow a flow diagram in order to provide a list of chronological steps that are taken to perform this operation.
Right. So now I'm gonna be explaining the crew balance chart and productivity analysis part. So for the crew balance chart, before we can draw out the crew balance chart itself, we need to identify which workers we are going to analyze. So in this slide here, I'm highlighting 4 workers labeled labor 1, 2, 3, and 4, and as well as the driver. So there's a total of 5 workers. In the next slide, there is the crew balance chart for the 5 workers involved. As you can see, worker 1 has the most idle time, and worker 4 also has idle time, although not as much. This can be improved in the improvement analysis part of the video. Moving on to the productivity analysis, we have assumed from the video, after analyzing it, the dimensions of the geotextile installed per cycle to be 800 square foot. And by referencing RS Means 2018, we have calculated the total labor cost and equipment cost to be $335.4 per hour. Dividing this number by the total amount of geotextile installed per hour will give you the unit cost, which is $0.01165 per square foot of geotextile.
First of all, let's look at the flow diagram and process chart. From the flow diagram and process chart, we can see that the operation which we are analyzing is basically the installation of the geotextile floor for a certain area on the construction site. The operation can be described in the following steps. First, the driver drives the truck with geotextile wrap on it to an allocated position. Then 3 workers, 1 on one side and 2 on the other side, pull the geotextile out to cover the allocated area. And finally, the installation cycle will be done in several steps of reposition the geotextile, securing the geotextile, and trim the geotextile. Moreover, we found a lot of problems with the existing operation, such as the idle times, uneven distribution of the workload among the workers, and the waste of labor. We also found solutions for these problems, such as increase the supervision on site, clarify the tasks that are expected of the workers, and reallocate the job among the workers. However, there is no nostrum that can solve these problems all at once. To find the optimum operational plan, we have to closely based on the situation we are facing.
Improving the observed activity was not difficult due to the large amount of time some of the laborers wasted standing around idle that we could reduce. This reduction could be achieved by having the laborers following specific cycles. For our proposed improvements, we decided first to do one model in which we kept the same crew size but optimized the cycle time. Second, we did one model in which the crew size was decreased from 5 laborers to 4 laborers. And finally, we changed the width of the geotextiles for our third and final model. For proposal 1, the crew is the same and the same activity occurs. We just gave specific tasks to each laborer. From our diagram, you can see 2 laborers constantly walk the geotextile out and return. 2 switch off between driving it and walking and adjusting the geotextile, and the final laborer folds and readjusts the previous geotextile. From our production analysis, we concluded that we could achieve a productivity of 8,229 square foot of geotextile laid per man hour, about 150% of the original productivity. The cycle can lay out and straighten 1 strip of geotextile the length necessary in 70 total seconds, 30 seconds shorter than the live crew.
The unit cost per square foot for this model is 1.17 cents per square foot, and it would not cost the company any extra unless management on site is necessary to ensure these specific cycles are followed.
For our second proposal to improve the current activities, we suggest to decrease the crew member size to just 4 laborers. By optimizing the crew balance chart, we are able to shorten the cycle time to 80 seconds. From our crew balance chart, in each cycle, we will have 1 laborer working on just carrying the geotextile and walk back. 2 of the laborers will alternate to help carrying the geotextile, folding and cutting the geotextile at the end, as well as walking back and adjusting the sides of the previous laid geotextile membrane. Lastly, we have the last laborer will be focusing on folding the geotextile, readjusting the previous ends of geotextiles, and also moving the truck forward. Since the duration is shorter and having a smaller crew member, we are able to get an output of 3,600 square feet per hour and a productivity rate of 9,000 square feet per man hour. For the total labor and equipment cost, it would be $264 per hour, and the unit cost would be about 0.0073 per square feet. For proposal 3, we decided that using a 12.5 feet wide geotextile rather than the original assumed 10 feet, and we will keep the same crew member size as proposal 1 with 5 crew members. So all the laborers in this proposal will be doing the same thing as in the proposal 1. In all, in a productivity standpoint, we are able to get an output roughly about 51,000 square feet per hour and a productivity rate of roughly 10,000 square feet per man hour. The total labor cost and equipment cost would be about $327 per hour and an unit cost of 0.0064 per square feet.
To summarize, the length for one cycle with 5 people on the crew, consisting of 1 truck driver and 4 laborers, was determined to be 100 seconds. The productivity was 5,760 square foot per man hour. Total labor and equipment cost was $335 per hour, and the unit cost was 1.165 cents per square foot. The issues with the productivity was that there was too much idle time, an imbalance of work between the laborers, and that there were 3 laborers pulling on the geotextile when only 2 were necessary. All of the issues listed could have been resolved through proper planning beforehand and supervision during the activities. Even if all of these issues were fixed, it still may not have been the best method in terms of increasing productivity. We have proposed 3 possible alternatives, all of which yield a smaller unit cost and a higher productivity. The first method, as mentioned, is to optimize the original crew balance using the same 5-man crew. The second method is to decrease the crew size to 4 laborers. And the third method is to increase the width of the geotextile from 10 feet to 12.5 feet, still using the 5-man crew. We conclude that the third proposal is the most effective because it leads to the highest productivity at 10,286 square foot per man hour and the lowest unit cost at 0.636 cents per square foot. This is our proposal. We are Team Parsons Brinckerhoff. Thank you for watching.